Good morning, good afternoon, good evening. Welcome to the second part of the numerical example, which is solar PV energy production estimations, which is part of lecture 4. So you need to go through all the three different parts that make up lecture 4. So come with me as I take you through this lecture. So just a recap, in the last part, we looked at what data availability and also comparison between the actual energy produced and also the estimation using the triangle formula. So since you can know the installed peak, with the calculation, we found that the answer is within 97% of the actual production, and the error is about 3% less than the actual production. So we concluded that the triangle formula is applicable for design work. So if we also do recap, what is the triangle formula? So this is an extract that we obtained from the daily cycle of a solar PV panel. So we are looking at the daily irradiation hours, which is the base of our triangle, and also the solar power peak. So we're able to say that the area of the triangle gives you a quick design parameters. Height is the solar power maximum or the peak, and the base is the hours of irradiation or production. And I should mention that for design, we actually look at the minimum in a day throughout the year. So this is from what we have. We have the energy half base times height, which is time from start to end of our production cycle. And then we also have the PV peak stroke maximum. So we want to apply to numerical calculations and also design problems. So we look at the scenarios. Here are the three different scenarios. We consider the energy consumption for three different houses in Lusaka, Zambia. One house has got 1,000 kilowatt hour per month. The second house has got 870 kilowatt hour per month. And the third house has got 420 kilowatt hour per month. So the question is, we have to estimate the required solar peak value in terms of panels that we must install on the three different houses so that we are able to sustain the energy that is actually required. So we convert the energy per month to actually the energy per day for the different houses. So we consider the cycle of the month to be 30 days. So we divide our energy per kilowatt hour per month by 30 to get what each of the houses need in a day. So we find that we need about 33 for the first house, 29 for the second house, and 14 for the third house. So these would represent high consumption house, medium consumption house, and lower consumption house. So when we move further, we actually apply our method. So in this method, what we have is the energy that a house requires in a day: 33, 29, 14. And then we pick 7 hours as the hours of production when it starts in the morning and also as it ends later on in the day. These 7 hours for Lusaka is actually considered for the months where there is solar irradiation, and also solar production. One thing I should also mention here is that this is not the ESH or the equivalent sun hours that we are using. We actually consider the entire cycle from start to end so that we are able to apply to our triangle formula. So for the first house, we need about 9.5 kilowatt peak. For the second house, 8.3 kilowatt peak. You can actually see that 29 and 33 across. And then when we look at 14, we need 4 kilowatt hour peak. So the design decision will actually be for 9.5, we will consider 10. For 8.3, we will consider 9. And then for 4, it's not 4 point something, it's not 4.2, 4.3. So we consider 4 as it is. So now we have these design values. How sure are we that these are close or confer with what had earlier been stated, where we are within the design parameters of the actual production? So we move on from what we have. We get to a software implementation. We've calculated 4 kilowatt peak as what is needed. So if we consider the 14 kilowatt per day, 420 kilowatt per month, this will roughly give us about 5.04 megawatt hour per year of consumption that is needed for this house. So we implement this small residential system into a software. So installed capacity, we say 4 kilowatt. Tilt, we use the default, which is 18 degrees, and this holds for Lusaka. Of course, when we move and follow the tilt of the house, and then of course, Lusaka is in the southern hemisphere, so the panels can face either north or eastwards. So I did the simulation and results were obtained. So this is actually what we get in terms of the values, the average values in a month per day. So this is average. So in a month, you can actually have the higher value, lower values for certain, but then we consider the average value. So we see that on the sum per day, we actually have the lowest of 15, which is higher than what we actually need on average per day. So we begin to see that our design formula is actually very much useful. You can meet a client, you can meet someone who needs your assistant somewhere in a plane, in a bus, in a vehicle. You can quickly do the design and tell them, okay, this is the parameter that you need to consider if you want to satisfy your consumption. So which gives us an upper hand to say we need energy consumption either per day or per month or per year to actually utilize our method, because 7 hours is not the minimum. You can easily get this information. Then from the software, we also see that this system will actually give 6.8 megawatt hour per year, which is higher than 5.04 megawatt per year by around 1.7 megawatt. So this can also help in the planning aspect because the load might grow over time. So when the load grows and requires about 6 an additional megawatt, then the system does not actually have to change. So this shows how we can actually transition from having the consumption per month, we go to per day, and then apply the formula. If you have got the consumption per year, So you actually divide by the number of days in a year to get per day. Then you can work with that design to actually determine your actual peak values, and also use what I call a rule of thumb. If you get a value of 0.2, 0.3, 0.4, it's better to go to a standard or to go a bit higher depending on your per panel configuration, because you can have 250 watts, you can have 300 watts, you can have 270 watts, you can have 320, you can have 340, you can have 360, you can have 400, 420. Now it's up to, I think, 710 watts. So your configuration in terms of the strings in series or parallel arrangement, which we'll come to later on, will dictate, but what you actually install should be a bit higher if what you get is not an actual whole number. Thank you very much for paying attention and also going through these three different parts to enable you understand us utilizing the triangle formula. So the next part we look at, which will be a bit quicker, is actually what is applicable in most books, what is found in books. So from myself, thank you very much for attending the lecture 4, numerical example 2. Subscribe, like, and share this knowledge. And if you have got questions, send to inokururio1@gmail.com. I would want to hear from you. I would want to hear you from India, from USA, from Zambia, from Africa, from Australia, from Asia. I would want to hear your views, questions, so that together we can learn and share knowledge. Thank you very much. From myself, it's bye for now.